Greetings, one and all. I am Nandh, Kishore, the narrator from Sri Subramanian College of Engineering, Chennai. At the outset, we would like to thank the organizers of ICCIM 2021 for giving us an opportunity to present our project. Our project is titled Design of High-Frequency Transformers Using Genetic Algorithms. The objective of our project was to achieve an electrically and physically viable design of a high-frequency transformer with optimized design parameters that can be applied as the AC link in a dual active bridge DC-DC converter. Finally, we wanted to optimize the design of a 20 VA single stage 24/12 volt 1 kHz transformer and build a prototype model and implement it in a converter that facilitates flow of power from source to load. This work proposes a design and optimization methodology of a high-frequency transformer that can account for its leakage inductance and losses. The major advantage of the suggested design procedure is that it proposes to the designer a set of optimal transformers instead of a single solution, since it optimizes not one but various parameters. The process of optimization is done with the aid of genetic algorithm, whose working is governed by Darwin's theory of evolution. Even in the case that the user wants to vary one or a few parameters, another optimized transformer or a set of optimized transformers for the new values can be obtained. Certain aspects of design, such as the core selection and core dimensions, are dependent on user requirements and don't have any fixed procedure to be optimally selected. So the solution for such problems is the use of stochastic optimization techniques. Stochastic methods are capable of handling a large number of variables under different equality and inequality constraints. They can generate fast converging solutions, and they function by incorporating the randomness into the optimization process, which is quite essential and is similar to the biological process of mutation. What we are doing in genetic algorithm is that genetic algorithm is a search-based optimization technique based on the principles of genetics and natural selection. Optimization refers to maximizing or minimizing one or more objective functions by varying the input parameters. In GA, we have a pool or a population of possible solutions to the given problem. These solutions then undergo recombination and mutation, similar to natural genetics, producing new children, and the process is repeated over various generations. Each individual is assigned a fitness value, and the fitter individuals are given a higher chance to be and yield more fitter individuals. This is in line with the Darwinian theory of survival of the fittest. In this way, we keep evolving better solutions over generations till we reach a stopping criteria. The various steps involved in GA are encoding, initialization, evaluation, selection, crossover, mutation, iteration, and decoding. In encoding, we map the genotypes of phenotypes. That is, we map the real-world variables into computational variables that can be input to the computer. The second process is initialization. Initialization refers to generating the population or initialization of the sample space. The population size depends on the nature of the problem. Often, the population is more populated with the solutions that we find or where the optimal solutions are more likely to be found. The third step is evaluation. The third step of the genetic algorithm is evaluating the fitness value of each individual through a fitness function. This helps create a quantitative base to compare individuals with each other. The fourth step is selection. During each successive generation, a portion of the existing population is selected to breed a new generation. Generally, the individuals with high value of fitness functions are selected for this process. Next comes crossover. This is analogical to the biological crossover process upon which genetic algorithms are also based. Crossover is a process of taking more than one parent solution or solutions and producing a child from them. Mutation. Mutation is a genetic operator used to maintain genetic diversity similar to biological mutation. Mutation may be defined as a random tweak in the chromosome to get a near solution. Mutation enhances the capability to produce more optimal solutions. Hence, the solution may change entirely from the previous solution also, but it may be more optimized. Then we iterate the above processes again and again until the solution reaches a saturation limit or the fitness value is more optimized. Then finally, we decode the genetic algorithm, wherein the final solution is decoded back to the phenotype, that is the real world variables. The design problem requires minimizing the mass or overall dimensions of the core and windings, as well as the loss of the transformer, while simultaneously ensuring the satisfaction of a large number of constraints. The design parameters of the transformers are classified as system requirements, pre-parameters, and parameters. After obtaining the ranges and options over which the pre-parameters can be varied, the genetic algorithm is coded to genetically select the fittest pre-parameters. These parameters are used to complete the design calculations and obtain the design and specifications of the intent to optimize the pre-parameters, including the window utilization factor and the flux density. Practically, for our 20 VA single phase 24 by 12 volt 1 kilohertz transformer, we gave the allowable temperature rise to be 50 degrees, minimum efficiency to be 90, and the saturation maximum flux density to be 1.2 vapor per meter square. Using these inputs, the optimized values of design given by the GA are as follows. For design of the core, it minimizes the area product, core volume, core area, transformer current density, length of meter, inner diameter and outer diameter, and height of core. Minimization of the overall dimensions also means there will be a subsequent reduction in the cost and the space of the transformer. So it is quite economical. Core flux density and core loss are optimized. The design of primary winding and secondary windings are also optimized because the number of turns and subsequent primary copper loss and the secondary copper loss and the area of the primary winding and secondary winding are all optimized. Finally, the performance figures expected by the customer are found to be within the limits given by the customer. The expected temperature rise was to be lesser than 50 degrees, but the optimized design gave only 13 degrees. The total loss was also quite less, and subsequently the percentage efficiency was also quite high, satisfying all the constraints given by the customer. This optimized transformer was implemented in a DC-DC converter as follows. The voltage levels are adapted at 24 volts on the primary side and 12 volts on the secondary side. The prototype was developed to run a small load of LED. Finally, an isolated DC-DC converter was constructed without any phase shift, since it's a prototype that facilitated the flow of power from the source to the load. These type of zero phase shift converters can be used for battery charging applications in EVs or aerospace applications. Upon supplying 24 volt DC from a regulated power supply transformer, a bidirectional wave that can be approximated nearly to that of a square wave is obtained. The wave obtained is influenced by the charging and discharging of the input and output capacitances of the MOSFET. That's the main switch, whose capacitance values are as indicated in the data sheet of the manufacturer. The gating or the pulses of 1 kilohertz frequency were obtained from the token. This was the practical inverter output wave that we obtained from a CRO. The rising and falling areas are clearly demarcated due to the internal capacitance of the FET. The hardware simulation of a dual active bridge converter is as shown. We approximated the optimized HF transformer to an equivalent inductance that is shown as the AC between the converter and the inverter. The output voltage across the load that was expected to be obtained was derived from the PSIM software, and this was the final output wave that we obtained from the hardware that matched the waveform of the expected output, and the rectification efficiency from the hardware was found to be 96%, which again matches the values validated by the genetic algorithm. The application of this dual active bridge converter with an isolation transformer, that is the HF transformer, are manifold. They are applicable in DC power microgrids. It's a high voltage DC charging for electric vehicles, and they are especially useful in systems where weight and size reduction is critical, such as traction, offshore wind power, and EVs. Especially in DC power microgrids, we connect a battery energy storage system to the DC bus. So this provides high level of reliability and resilience to grid disturbances. It also facilitates bidirectional flow of current. The excess energy can be fed back to the source. So this in turn increases the efficiency once again. This is also now used in DC charging of electric vehicles more commonly. Moving towards electric vehicles indicates that the society is moving towards a greener and environmental friendly mode for autos. The future scope of this project include the hardware implementation using synchronized rectifying and inverting by implementing control using Arduino, PAC or STM32 controllers, achieving bidirectional flow of power, and optimization of the core type and core material which are fixed for this. Concluding, the design of high-frequency transformers was optimized implementing bio-inspired optimization algorithm, that is, the genetic algorithm, taking into consideration physical, thermal, and electrical constraints. A working dual-active bridge converter was designed and simulated using the previously determined high-frequency isolation transformer specifications. The converter was found to exhibit low power loss and good output regulation in comparison to non-optimized transformers. A hardware model of a dual-active bridge converter was implemented with the approximation of an inductor instead of a transformer for the rating of 20 VA, 1 kHz, and 24 watt 12 volts. Thanks for honoring us. Thank you for selecting our project to be presented in the ICC IML 2021 conference. Thank you once again.